Hi guys, today we're going to discuss moments. We're going to do beams. We're going to have a look at one of the papers and see how we can solve these questions. Specifically, it's engineering science N4, but you will have noticed if you're at N4, obviously you will have done your N3. You will have noticed there are beams at N3 as well. So N3 and N4 is exactly the same. The difference will be at N4, you go one step further, you do a bending moment, where at N3 you end up with a shear force diagram, but the concept, the basics, everything remains the same. So whether in N3 and N4, you are welcome to take part. Right, let's have a look at one of the questions here. I think it's from one of the previous exam papers. I think if I'm reading this correctly, it's an English paper. It's from November 2018. Right, we're going to specifically go to question number 4, is the one on moments on beams. In this case, you will have noticed as well, sometimes you find that the beam is drawn for you, but most of the time they give you in a word form. You have to draw the beam yourself. Right, let's go through this one. Question 4, they say here a beam ABCDE with A on the left hand side is 10 meters long and simply supported at A and D. Point loads of 50 newtons and 30 newtons are at B and E respectively. AB is 2 meters, the length from A to B is 2 meters, and DE is 2 meters. An evenly distributed load of 2 newtons per meter is between A and D. Right, I've got the beam drawn up here. Okay, let's quickly discuss that one. Obviously, you've got to draw the beam. You're going to get a mark for that, for drawing a beam. As you can see, they said the beam is A, B, C, D, and E. It's a beam. They said it's 10 meters long and is supported at A and D, meaning that A and D, they are pointing up. It's supporting this horizontal beam at A and at D, as you can see on the diagram. And they tell us they've got 2 point loads, 50 kilonewtons and 30 kilonewtons. Right. Then they told us that the 50 kilonewtons is at B, as you can see, put at B, and the 30 kilonewtons is at E, as you have placed them. And the length between A and B is 2 meters, and the length between D and E is 2 meters. And we all know that the total length of the beam is 10 meters. The beam is 10 meters long, meaning if we've got 2 meters here and we've got 2 meters here, it means the remaining length between B and D will be 6 meters. Right, and furthermore, we are told that between A and D, we've got an evenly distributed load of 2 newtons per meter. As you can see here, we've put that spread load here between A and D. Right, so far that is what is asked for us. I think that one was straightforward and clear. Let's have a look at what is asked from us. The next question, what is it all about? The next question you'll notice here, we are asked, obviously, first draw the beam, like as we have discussed, calculate the reaction forces of A and D. It's quite one as well. We have done that from, I think, from N1, whereby you calculate the direction of one support, you go to N2, you get to work on 2 supports, you go to N3, then you get the distribution load get introduced and the shear force diagram. It's the same thing here. Right. We're going to use law of moments. The law of moments says the sum of clockwise moments about a point is equal to the sum of anti-clockwise moment about the same point. Right, we're going to take moments about A. There we say moments about A, meaning we're going to check all these other forces, whether they are clockwise or anti-clockwise to A. Right, we start with 50. As you can see, it's pointing down, take it to A. As you can see here, is this clockwise or anti-clockwise? You'll notice that 50 is clockwise to A. That's why we see we wrote it in the clockwise side. The length between 50 and A is 2. 50 kilonewtons times 2. That's how we got about that one. Is on the clockwise side. Right. We go to the next force is D. You can see we can't go this way because it's pointing up. We go this way, we follow it, we follow to A, D to A. You'll notice that D to A is anti-clockwise. That's why we wrote in the anti-clockwise side is D. What is the length between D and A? Is this 6 plus 2. It gives us 8. That's why we said here D times 8. Right, we got the next force. Is point load 30 kilonewtons. 30 kilonewtons. This is pointing down. If you follow there to A, we said moments about A, the meaning we are working to A. If you follow D to A, you'll notice is clockwise. As you can see, it's pointing down. You can't go that way, therefore you have to go this way, this way, this way, this way, this way, and then all the way back, and then all that way again. You'll see it's clockwise. Then it's 30. The distance between 30 newtons and A is going to be 2 plus 6 gives you 8 plus 2 gives you 10. Well, that's why we have here 30 times 10. You'll notice it's also clockwise. It's on the clockwise side. You just add it there. Right, you can't say 30 times 2. No, because we are working to A. If we were saying moments about D, yes, you're going to say it's 2. But yes, 30 to A, then it's 10. Right, and then we've got a distribution load. Remember, guys, the distribution load is always working in the middle of its distance. Very important, note that. Right, now you can divide it and say from here to here is 2 Newton per meter. What is the length here? The length here is 2, which means it's going to be 2 multiplied by 2. It's going to give you 4. It's on the top. Obviously, the load for the top is pointing down. Right, if you go from here, you go there, you will notice there it's clockwise. It's going to be like this. It's clockwise. Right, now it's going to be 4 multiplied by half. I said middle of its distance. Half of 2 is 1. That's why I've got 4 multiplied by 1 here. Right, and then you notice from B to D, we've got another distribution load. Another distribution load here. It's 2 Newton meter. The length here is 6. It's going to be 2 times 6. That's why I've got this 12 here. What will be the length? Very important. You have to listen to this one. Half of it here at this distance, how much will it be? It's going to be half of 6 here. It's going to be how much? It's going to be 3 plus 2 to A. Then it's going to give you 5. Right. That's how we do that. Then you multiply the brackets. Then you add and you divide by 8, you'll get 58 newtons. That is the reaction that support D. Very important. The other way, guys, you can do it, you can work it from the total length of the distribution load. You can say the distribution load here is from A to D. Very important to listen to this one now. You now can say is 2, you multiplied by this distance here is 8. So if you say 2 multiplied by 8, it's going to give you 16. Right, now half of its distance is going to be 4. It's going to be 16 multiplied by 4. Right, you're going to have 64. Then you can have 64 plus 300. It's going to be 364. You add it by 100. It's going to be 446. You divide by 8. You're going to get 58. So you can work it out that way, or you can work it in portions. It's up to you the way you prefer to work out that one, but it's exactly the same. Right, now we're going to say moments about D, meaning we're going to check all these other forces, whether they're clockwise or anti-clockwise to D. It's moments about D, same principle, law of moment. Sum of clockwise moment about a point equal to sum of anti-clockwise moment about the same point. Right, now, if you check this one, 30 to D, now you can see here, it's going to be like this. It's clockwise. That's why we've got it in the clockwise side, 30 times 2. Now from 30 to D is 2. Remember, before it was 30 to A, now we said moments about D. That's why I only say 30 to D here. Then we take this distance is 2. Right. Then let's check this one to D, 50. As you can see, it's going to go like this, like this. Therefore, it's going to be anti-clockwise. That's why I've conceived for on the anti-clockwise side is 50. What is the length? The length is 6 from 50, which is at B, to D. The length here is 650 times 6. Right, then we check A is pointing up. As you can see, it's going to go this way, this way. Is it clockwise or anti-clockwise? You can see that is anti-clockwise. clockwise. Right, that's why we've got apologies. Let's go through this one again. A, look at the arrow is pointing up. What is this, guys? You can see it moves like a clock, moves like a watch in the direction of the watch. That is clockwise. You'll agree with me, that is clockwise. Right, we've got it on the clockwise side. It's A multiplied by 8. The distance from A is 2D is 2 plus 6 is 8. Right, then we go to the last one. We've got the distribution load. Same, you can split it or you can work it as one. Right, meaning if you split it, you're gonna have 2 multiplied by this length here. It's gonna be 4. Half of 2 meters here is 1. Then it's gonna have 4. This 4, remember, is always the force here is pointing down. Is gonna be anti-clockwise to D. That's why we've got 4 on the anti-clockwise side. It's working on the half of its distance. You're focused only on this distribution load here. It's 4. Half of its distance here is 1, plus the remaining distance to D, which is 6. Then we get to 1. This 1 plus 6, then we get 7. That's how we got to this one. Then we've got the remaining distribution load here is this one. You're gonna have 2 multiplied by 8. This length is 6. Then it's gonna have 12. That's where you get to this 12, and it's always pointing down as well. Then you can look at the direction there. It's also gonna be anti-clockwise. That's why it's on the anti-clockwise side. The distance always work on the middle of its own distance. The distance from here to there between for this distribution load is 6. Half of that distance is 3. That's why I'm gonna have it multiplied by 3. Or simply you can take this distribution load as 1, guys, as 1, meaning you're not going to have this one and this one. You're going to combine them as 1, meaning you're going to have 2. You multiply it by the total length here, which is 8. That's going to give you 16. Half of the distance to D, so we're going to get 4. Going to give you 64. Right, meaning you're going to have 64 plus 300. You minus 60 from it, you divide by 8, then we're going to get 38 newtons. That's correct. Yes, 100%. Yes. Remember, you can work a distribution load in portions, or you can take it as one. We'll discuss the other beam whereby you'll see your distribution load. Maybe we've got a support here. Then we'll see that one, it turns out a little bit different. But in this case, guys, it was easy and straightforward. As we discussed, the concept remains the same. Right, now, as you continue, after calculating the reactions at your support, it's very easy, guys. Use Newton's third law to check if your answers are correct. Newton's third law says the sum of upward forces must be equal to the sum of the downward forces. Right, the upward forces, we only have got 2, which is the reactions of support, is A and D, which is 38 plus 58, they give us 96. The downward forces, we've got 50, the point load, we've got 30, the point load. The reaction, the distribution load here, 4, and the distribution load, which is here, which is 12. Then if we add them, we'll get to 96. You can see the upward is 96, the downward is 96. Therefore, it means that our beam is in equilibrium. In other words, is balanced, and we are certain that your answers are correct. Right, we go to the next question. The next question, you will notice it asks us to say, calculate the bending moment at B and D and at C, half D. Draw the bending moment and shear force diagrams. That is the third question. And when you draw those bending moment diagram and shear force diagram, you have to indicate on the diagram the values. Very, very important. You have to indicate the values. How do you get those values. Let's have a look at that. Right. Very easy, guys. Very easy, guys. Our bending moment shear force diagram, guys, they always start at 0 and end at 0. My advice will be, after you draw your beam, or before you draw your shear force diagram and your bending moment diagram, you must draw your beam at the top, then you've got your shear force diagram, then you've got your bending moment. It's going to be easy for you to do that, to calculate them and to follow their directions as well. Right, but anyway, we'll get to that point. Right, for now, we have to calculate the bending moments. The bending moments, guys, just like the shear force diagram, you'll start at 0 and will end at 0. Therefore, meaning the bending moment here at A will be 0 at the beginning and at the end will be 0. No, straightforward that one. Right, the bending moment at A is 0 Newton meter. We're not gonna stress much about that one. Right, the bending moment at B, you can start from left or from right. It's up to you which one do you prefer. Right. Apologies about that. If we start from the left end, we want the bending moment at B. Let's see. Right, how many forces do we have before we can get to B here? We've got this one. As you can see, it's pointing up. Therefore, the ones that are pointing up, remember, is positive. Right, it's A. How much of the value of A is 38? The between A and B, the distance is 2. It's going to be 38 multiplied by 2. Right, it's going to be 38 multiplied by 2. As you can see here. Right, we've got the shear, the distribution load here, which is 2 multiplied by 2 is 4. Remember the distribution load, half of its distance is 1. Then it's going to be 4 multiplied by 1. Then that's why we subtract this in the opposite direction, that one. Then we get to 72. Remember, we work from here, from A to B. You can't take 50 into consideration because you are working at B. You work everything before B. This one, you don't consider it. You can only consider it when you work at C. If you take bending moments at D, you can't consider the value here at D. If at A, you can consider this value, the value here. The same as at E. Right. Now we go to the next one, the bending moment at C. Right, we've got 38, it's pointing up, is positive. The length from A to C, right, is 2. From here, B to C is 3. Therefore, it's 2 plus 3, then it gives us 5. Then it's 38, which is A, multiplied by 5. We've got it, there it is. Right, now, we say minus, this one is in the opposite direction, it's pointing down. 50, from the distance from 50, point load 50 to C is 3. Right, apologies, this is just a print error. This is a minus sign. Please, this is a minus sign, it's a print error. Right, you will see we've got a distribution load from here to there. Our length from A to C is 5. We have discussed that. Then it's going to be 2 multiplied by 5. Then you get to 10. Half of its distance, half of 5 is 2.5. And then you do the mathematics there. You multiply the brackets, and then you subtract. You get to 50 Newton meter. The bending moment at C, same as well. Apologies, bending moment at D. The bending moment at D is going to have A, which is 38, it's pointing up. You multiply by the distance there, is 8. It's 2 plus 6, then it's 8. Right, then we've got minus 50 multiplied by 6. Then the distribution load is going to be minus the distribution load of 2 multiplied by 8, which is going to give you 16. And then the length here is 8. Half of 8 is going to be 4. As you can see, half of 8 is going to be 4. This is from 2 multiplied by 8, and then you do the math, then we get minus 60 Newton meter. Then the bending moment at ease at the end, we discussed that, we're gonna get it's 0. Right, now let's go to drawing of the shear force diagram and the bending moment diagram. Like we said, I always advise you have to draw your beam here at the top. It's going to be easy for you. You can use your scale here. You can use the scale, or you can roughly draw it like as it is here. But very, very important, if you draw it like this, it means you can't have 38 here and then 34 at the top. No. So if you're not sure about that, simply use the scale. Right. You'll notice at A, we've got a force pointing up of, that's why it's going up. It's pointing up. That support is 38 Newton meter. You go up 38 Newton meter. From A, we want to move B. If you see a line that is not straight, you must know there is a distribution load there. And the distribution load there is 2 Newton meter. And the distance here is 2. Therefore, is 2 multiplied by 2 is 4. Therefore, this one is going up and that other distribution is going down. Then we're going to subtract 38 minus that distribution rate of 4, opposite direction. Then we're going to get to 34. That's how we got that 34. Right, and while we are here at 34, right now, we must go down. At 34 is at B. B is pointing down 50 kilonewtons. You must go down 50. You already have got 34. To get to 50, you need 16 more. That's why it's on the negative side. Right, and from B, from B, C and D is just a distribution load there. A distribution load, you'll notice that the distance here is 6. If you can check that on your beam, is 6, and the distance is 6. The distribution load is 2 Newton meter. If you say 2 multiplied by 6, you'll get to 12. That's when you move from 16, you go 12 more down. You're gonna get 16 to, you add 12 more down, you're gonna have 28. While you are here, you must go at D now. You are at D now, you must go up 50. You already from here to here, you already moved 28, then you need the remaining, which is 30. This will give you 50. Right now, from D to E, you've got no distribution load. As you can see, when you see a straight line, you've got no distribution load. Right, meaning we go straight line here, no distribution load, but we must go down 30. And if you go down 30, you'll see you'll end up at 0. The 30 is the point load at E. Right, very easy. What you're gonna do in the next session is we're gonna discuss the shear force diagram. How can we convert it back? We just have a shear force diagram, we draw a beam. By just having this shear force diagram only, you can draw a beam. You can see you've got a support here, you went up. Here you've got a distribution load. Here you've got a point load. Here you've got a distribution load. Here you've got a support. Here there's nothing. And then here you've got a point load. By just looking at the shear force diagram, it will tell you what is happening there. Right, the bending moment diagram is easy, guys. You have calculated those values. Start at 0 and at 0. And you'll see from A, we need to go to B. We need to go to B. We have also, remember, if you bear in mind, we have also taken into consideration all the distribution load and all that when we did our calculations. And you'll notice from A, we move to B. See there it is B. We move to B. 72, it was positive, a positive value. And you'll notice it makes a slight curve here. It means there's a distribution load. Now, from B to C, there's a distribution load. There's a distribution load. And then at B, sorry, apologies, at C, we got 15. At C, we got 15. That's why that value is, it was a positive 15. And then from C, we must go to D. At D, we got a negative value of 60. And we still have got that distribution load. You'll see here it's not a straight line. Now, from D, we must go to E. From D, we must go to E minus 60, and then E will end at 0. Right, and you'll see here, you'll notice here, this one, it goes on a straight line, means there was no distribution load there. Right. It was bit easy, quite easy, this one. So what you're going to do is you're going to have, in the next session, we're going to have a look at the beam whereby you've got your distribution load that it goes over a support. Then you see that one is quite challenging. And also, we're going to take a shear force diagram. By looking at the shear force diagram, we draw a beam from that. So guys, it's straightforward. You can take more practice. Practice makes perfect. We're going to have more and more sessions on this, and so that everyone, we can be guaranteed you've got plus 15 marks that you're going to earn fairly in the exams. Then before we move to the next chapters, to make sure that we all get our distinctions. Thanks guys. I hope you enjoyed that session, or this session rather.